Okay, so in this video, we're going to look at how to work with probability distributions in R. Now, the probability distributions in R are basically broken up into four different flavors. D, the distribution, P, then the distribution, Q, then the distribution, and R with the distribution. And so we're going to look at particularly the binomial distribution as our first test case. So D binom, so this is our first example, binomial distribution of the D type. We're going to specify the number of trials, the number of successes, the number of trials, and then the probability. And if we run that, then it's going to calculate our probability for us. So kind of keep this in mind. This is, the syntax is X, N, and then P. For each of these distributions, the syntax obviously will have different parameters that you have to enter. And so you may need to look at the documentation for other kinds of distributions to know what kinds of probability, what kind of inputs they require and in which order. If you go online and you look for examples of lists of other available distributions, then there are such lists that you can look for. This is our binomial distribution, and every one of these probability distributions has these four flavors of functions that you can use to calculate. Obviously, the continuous ones are used a little differently than the discrete ones, binomial, for instance, being discrete, whereas normal distribution being continuous. But this is not even really an exhaustive list. There are so many. If you can think of it, there are going to be distributions that you can use for these behaviors. Now, if we go back to R, the D binom is the discrete probability. So it's the probability, in this case, of getting exactly 6 heads, for instance, in 10 coin flips, where the coin has a probability of 0.5. Now, we can use the D binom or the D type of any sort to create a graph of the distribution. So I'm going to store my outcome. So in this case, I'm going to calculate a sequence from 0 to 10, going by 1. And that's just, since I'm doing 10 coin flips, these are going to be my possible outcomes. 0 through 10 are the possible numbers of successes I could have. And then Y is going to calculate the probability. And I'm going to do that probability calculation for each of the input values. So here, X is going to run through my sequence of X's, calculate the probability, and then store that in my Y variable. And then in base R, I can go ahead and just plot X and Y, and it'll just give me a graph, a point graph of the plots. I could probably also make a bar graph of this if I really wanted to, which would be more typical for a probability plot for a discrete variable like this. But this is fine. It gives you the clear idea. The probability starts low when you're talking about 0 successes or a lot of successes, and it peaks around 5, which is the expected value of the sequence. You would expect that to be the most, and then the next most on either side is 4 and 6, which was the example we calculated earlier. Now, if I want to basically do the same thing, but with the cumulative probability, then I'm going to be using the P binom function. So the syntax is basically the same, but instead of D, I'm going to use P. And so when I run this, you can see the probability is much higher because this is the probability of getting 6 or fewer heads. Not just 6, not exactly 6 heads, but 6 or fewer heads. And so when you're doing continuous probability distributions, you're almost always using the p version of this function. When you want to create a graph of the cumulative distribution functions, you can use the same trick that we did before. We're going to create our list of possible outcomes from 0 to 10, since that's the example that we're working with. And then we'll use the p-binomial to calculate the probabilities. And then when we get to 10, we should expect that the cumulative probability would be 1. And I didn't run the intermediate lines, and so there we go. So again, it starts out small, but now we're adding probability, so it only grows. The steepest rate of increase is when you get to 5, and then it slows down and then levels out. And again, you're at 1 by the time you get to 10. Now, the Q binomial is going to be the inverse function. And again, the Q is the inverse function for any of these probability distributions. Now, for the discrete cases, this is a little trickier than the continuous cases. It finds, in this case, the first discrete value whose cumulative probability meets or exceeds the specified probability. So you would need to get at least 8 successes in order to have a greater probability than 0.95. And we can actually see what the actual probability is by actually running that value. And it's 98. So you've jumped past it a little bit, but 7 would be too small. So that's not quite at 95. And so the first discrete value that exceeds 95% would be 8. So that's how you interpret what you're getting. In the discrete case, again, you have fewer options, and so you have to exceed that value, not just get really close to it. In the continuous distribution, they can be more precise, and you'll get a lot closer to the true cutoff. And then the final flavor of our probability distributions are the R flavor. And in the R is for random sampling. And so we can specify the number of samples that we want, and then specify, in this case, the number of trials and the probabilities. So this would be basically, we're going to find out if we were to take a fair coin and flip it 10 times, and then calculate the number of successes, and then repeat that process 100 times, what would be the result of that process? And we're going to get a list of the types of successes that we got when we do that. So you can, for instance, then go ahead and find the average of this list. So we could find the mean of our random sample, for example, and it's about what we would expect it to be. It's 4.99. Again, the expected value is 5, and so this is pretty close to what we would expect it to get. Again, it's a random sample, so it may not always give you exactly the expected value, but it should be very close. Now, just as an extension, this was the discrete case. We can go on and use the continuous case. And so I want to just do one example. For the continuous cases, we don't usually use the D type because that is actually the PDF version, not the cumulative, but in the discrete case, it gives us the discrete individual values. But in the continuous case, basically you can only use it to create a graph. And so that's actually what I'm going to do with this, is I'm going to create a graph of the normal probability plot using the D norm, because that's its purpose. when you're dealing with a continuous distribution. So I'm going to create a sequence from -10 to 20, and I'm going to go by 0.1. And then my y is going to be d norm of that sequence. And I'm going to specify the mean to be 5 and the standard deviation to be 4. So this is not a standard normal. And then we can plot x and y. And again, this is just base R. It's plotting points on top of each other, but you can see that this does give you a nice continuous looking normal distribution by essentially plotting the height of the PDF for a lot of values, and then that all flows together. You can certainly do this for other kinds of probability distributions. For different distributions, of course, the range of the values will differ a little, and so you may have to adjust the sequence that you're using and the parameters that you're specifying, but you could easily plot different probability distributions for different parameters so that you can see what they look like, and you can calculate probabilities and inverse probabilities for all kinds of things, including the normal distribution, the t-distribution, the chi-squared distribution, and other kinds of distributions. But again, they all work the same way. D is the discrete case, R is the random case, P is the cumulative case, and Q is the inverse case.